So when we last talked, we left off with the fifth postulate, and people were saying, yes, it's a postulate. No, it's not. So what was the deal with the fifth postulate? Remember, it says that through any point outside of a given line, only one parallel line can be drawn through that point. So what we're dealing with when we go to non-Euclidean geometries are geometries where the surface of the plane is no longer flat. It can now be curved. So believe it or not, the first geometry that was discovered was actually a pretty complicated geometry. It's called hyperbolic geometry. And you can see that it looks sort of like a saddle. And if you put a lot of these little saddles together, and if you ever get crazy with crochet, and I actually do crochet, you can end up with some crazy shapes. So if this is your surface right here, it doesn't look anything like flat paper. So what happens when I flatten out a hyperbolic geometry? Well, you can see here's one line, believe it or not, that's a straight line in hyperbolic geometry. And here's a point not on that line. So there's the point. I can actually have two lines that are parallel at different points. So you see there's a parallel line, there's a parallel line, and both of those lines pass through the same point. Are you expected to actually draw these points? I doubt it, but it's kind of cool. This was actually the Lobachevskian parallel postulate, where you can have two parallel lines going through one point. Now, the main thing to know about hyperbolic geometries is that the triangles get kind of squished together in the corners when it's all curved. And so that the angles don't add up to 180 degrees anymore, which, by the way, you learned in 6th grade. It's for the 180-degree angles. And not only that, lines on the surface may eventually diverge. So they don't actually have to be, parallel lines don't have to be the same distance apart. So with spherical geometry, if it were me discovering another geometry, and I didn't, I would have thought spherical geometry would have been more logical. Now, this is a video that shows the longest distance you can sail in a straight line around the world. I remember it starts in Pakistan. Oops, let me come back up. So we'll play this video right here, which should play. Oh, there we go. So this is the longest straight line that you can sail around the world. All right. What will that straight line look like when you unfold it into a kind of a map of the world? It's going to look something like this, which doesn't look like a straight line. So it was rotating, starting here, coming around, going to the other side, and then ending up somewhere in Russia. So started in Pakistan, going all the way up here. So when we get to non-Euclidean geometries, remember that planes and lines don't behave quite the way they did in Euclidean geometries. So if we look at a spherical geometry, one of the things with parallel lines is that they're not always parallel. So if I started walking due north from Texas, and another person started walking due north from, say, Florida, eventually we're both going north, we're parallel, but the lines will actually intersect. So parallel lines can behave very differently in a spherical geometry. Additionally, if you look at, say, a triangle in a spherical geometry, it can actually have more than 180 degrees in it. Here's a right angle, and a right angle. So spherical geometry is actually a little bit easier to understand. We see it when we deal with long distances around the Earth, and it's also used for satellites and GPS. For those of you doing the notes, you might want that. Applications of spherical geometries is right here. Now, this brings up another interesting geometry, which is called Taxicab Geometry. It's called Taxicab Geometry because taxis are not allowed to drive through buildings. They must stay on the streets. And which means, whoops, I keep hitting that thing, which means that it can't go in a straight line from here to here. All right? So if it can't drive in a straight line, distances are measured a little differently. Instead of doing what we'll do later, the distance formula, they just have to count the blocks across and the blocks up and down. Now this is a cool little thing. This won't be on your test. But this is a taxicab geometry circle. The reason is the taxicab has to drive the same number of blocks if it starts at the blue dot to any of these red dots. Here it goes 1, 2, 3, 4. 1, 2, 3, 4. So any of those red dots is 4 blocks away. Now the last one, and again, definitely not on a quiz or test. This is the Einstein space and time. So I just wanted to show this one to you. It basically depends on the gravity. So if you have a star that's very far away, another star is so big and the gravity is so strong, it can bend the light, which normally goes in a straight line. So that means that the star actually, even though it's here on the other side of the sun, it might actually look like it's up on top. So things that aren't quite as they appear.